The option, Training in Industrial Aspects of Wind Energy, is a web-page document, designed with several purposes. The first one is to present the main topics concerning the technologies used in wind energy elements. They are presented in a mind map, that starts, in the left top side, with concepts related to wind farms, and follows with concepts around wind turbines. The right part starts with the physical principles of the components and subsystems inside a wind turbine. Then follows, center right, the concepts about the elements involved in exporting the generated power and how this power is distributed to the grid. Another important area of required knowledge is related to the instruments used inside the wind turbine and the control center of the wind farm. Finally, there is a mention to a very important aspect, how the input power to these production plants are evaluated. Next item, in this page, presents the student with names of parts and subsystems, in an industrial-grade wind turbine. Follows another item with a short classification of the actual wind turbines installed in wind farms. They are presented according to their historical evolution. It is interesting to note that, although modern wind turbines may have a similar form as the older ones, there has been a big evolution on their internal subsystems. The oldest wind turbines models that still may be found in some wind farms, are of the family so-called fixed-speed, squirrel cage induction generator. Their installation finished before 2000. Their nominal power was lower than 300 kilowatts. A second wave of wind turbines had variable pitch angle, although still with squirrel cage generators, directly connected to the grid. These models are no longer installed in new wind farms. Their nominal power reached up to 1,300 kilowatts. In parallel, another technology emerged, to solve the problem of incrementing the nominal power, and supporting wind gusts, all without incrementing, heavily, the construction costs. The family name is called, rotor resistance controlled wind turbines. They also used variable pitch blades. There are still some, few, manufacturers that use this technology. The big change came with the so-called doubly fed induction generator wind turbine family. It constitutes the workhorse of wind turbines nowadays. In parallel, another wind turbine technology emerged, that uses synchronous permanent magnet generators, and requires a big power electronics equipment. Its market share is less than 10%. There are a number of variations in this approach, some using other types of electric generator. But regardless these variations, they are known in the industry as full converter wind turbines. The other significant detail is that this family do not use gearbox, a source of important maintenance costs in the other families. Next point in this page, named, Operational Wind Ranges, introduces the relationship between the wind speed and the generated electrical power. This function has an S form, and there is a maximum value for the generated power, limited by the generator and power electronic capabilities. This value is the nominal power. In modern wind turbines, the minimum wind speed to reach the nominal power is the nominal wind, and the generated power is flat above the nominal wind speed. In older, fixed-speed wind turbines, that power versus wind speed is not flat above the nominal wind. The actual form of this S function depends on the family of wind turbine, and, also, on the actual blade used. Logically, there are limits for the maximum wind speed that the wind turbine can handle. But there are several maximum values, that refer to several working aspects. The maximum wind speed for operation, is the maximum wind speed at which the wind turbine will operate continuously, is typically around 25 meters per second, or 90 kilometers per hour, equivalent to 50 miles per hour. The absolute maximum wind speed is the value at which the wind turbine will be cut out immediately if in operation. It is, typically, around 30 meters per second, or 108 kilometers per hour, equivalent to 60 miles per hour. There is also some maximum speed for temporary operation values, meaning that the wind turbine will continue in production, if already in production and the wind speed runs over the maximum wind speed for operation. There is a timer associated with this mode. There are other significant values of wind speed, in the operation of wind turbines. One is, the minimum wind for yawing, meaning the minimum value for the nacelle to orient itself upwind. This value is lower than the minimum wind for Qton. Qton is the name of the operation that the wind turbine starts when, being disconnected from the grid, detects that the wind speed is enough to let the blades to start rotating, to finally connect the generator to the grid, and start generating power. There is another value of wind speed related to the cut-in process. This value is above the nominal wind speed, near the maximum wind speed for production. Depending on the wind turbine model, and on the historical wind regime at its location, it may make economic sense not to start the cut-in operation at that high wind speed. This is because, the wind speed will rise above the maximum wind for production, as this may mean that, probably soon, and, if that happens, a cut-out process must be started, disconnecting the wind turbine from the grid. The operations of connecting, and disconnecting, the wind turbine from the grid, places mechanical stresses that may not be financially compensated by the generated energy in those periods. There are fixed-speed blade wind turbines, that contains two generators, allowing them to work at two different blade rotational speeds. According to this behavior, there is a wind speed above which the wind turbine should work using the big generator, and there is another wind speed value below which the wind turbine should work using the little generator. ACMSL has developed a set of real-time simulators, designed to complement the learning path for personnel in the areas of commissioning, maintenance and operation of wind turbines, and wind farms. One of their design goals is to facilitate a closest as possible to real experience, of the behavior of utility-grade wind turbines and wind farms. These simulators are complemented with specific tutorials, where the student can find theoretical background needed to understand the physical principles behind each of the sub-assemblies in wind turbines. The simulators act as workbenches, where the student may set different working conditions, like wind speed, wind direction, wind gusts, temperatures, pitch parameters, yaw parameters, etc. Those conditions may be within specifications, but can be also exceptional conditions, like, for example, very high winds. And even can simulate failures, like slow-moving pitch mechanism, leakages in the hydraulic system, etc. In every case, the student can observe the evolution of the internal signals in the wind turbine subsystems, and also the messages issued by the wind turbine controller. This set of simulators and tutorials is conceived as a didactic unit, with 4 consecutive steps. The first one, for the concepts in wind farms, all its constituent elements, the grid, the relationship with the weather forecast, etc. First step in the study of the different aspects, common to every family of wind turbines. The third one corresponds to a family of wind turbines that was a leap jump in the technology, key to understand the modern wind turbines. The fourth one, for the doubly fed induction generator family of wind turbines. This family is the workhorse of the market.